In 2013, 3 astronomers started counting galaxies. Simple enough, right? Point a telescope at the sky, tally up the galaxies, move on. But when they finished, something was wrong. There were not enough galaxies. Not by a little, by billions. They checked their math. They checked their instruments. They checked again. The numbers did not change. And then they realized what they were looking at. Earth, our solar system, the entire Milky Way. We are all sitting inside a giant hole in space, a void stretching 2 billion light-years across. And according to a study published just months ago, it might be warping everything we thought we knew about the universe. Let's back up. In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie published a paper in the Astrophysical Journal that should have made bigger headlines than it did. They used data from the 2-micron All-Sky Survey and the Sloan Digital Sky Survey to map galaxies in our cosmic neighborhood. What they found was disturbing. Within about 1 billion light-years of Earth, there were 20 to 50% fewer galaxies than there should be. The universe was not evenly distributed. There was a massive chunk of it that was just emptier. They called it the KBC Void, named after the 3 researchers who found it. And it is not small. At roughly 2 billion light-years across, it is 7 times larger than the average cosmic void. Think about that for a second. The Milky Way is about 100,000 light-years wide. This void could fit 20,000 Milky Ways across its diameter, and we are floating somewhere near the center of it. But here's where it gets unsettling. The discovery challenged something called the Cosmological Principle. This is the foundational assumption in physics that says the universe at large scales should look roughly the same everywhere. No special places, no cosmic neighborhoods that are dramatically different from others. The KBC Void said otherwise. It said we might be living in one of the emptiest regions of the observable universe. And for years, the scientific community largely shrugged. Interesting, they said. Probably a statistical fluke. Let's move on. But the void didn't go away, and neither did the problems it created. To understand why this void matters, you need to understand the biggest crisis in modern cosmology. Scientists call it the Hubble Tension, and it's been driving physicists insane for over a decade. Here's the problem. The universe is expanding. We've known this since Edwin Hubble proved it in 1929, but when scientists try to measure exactly how fast it's expanding, they get 2 different answers, and both answers are correct. Method 1 uses the oldest light in the universe, the cosmic microwave background. This is radiation left over from the Big Bang, about 380,000 years after the universe began. The European Space Agency's Planck satellite measured this light and calculated that the universe should be expanding at 67.4 kilometers per second per megaparsec. Method 2 uses what's called the cosmic distance ladder. Nobel Prize winner Adam Rees and his team at Johns Hopkins measure nearby stars called Cepheid variables and Type Ia supernovae to calculate expansion. Their answer? 73.04 kilometers per second per megaparsec. That's an 8 to 9% difference. Doesn't sound like much until you realize the statistical significance is over 5 sigma. That means there's less than 1 in 3.5 million chance this is random error. Both measurements have been checked, rechecked, and verified by independent teams using different instruments. The James Webb Space Telescope confirmed Hubble's measurements. The numbers are solid, so either our understanding of the early universe is wrong, or our measurements of the local universe are wrong. Or, and this is where it gets interesting, something about our location in the universe is messing with our readings. Enter the void. In July 2025, Dr. Indranil Banik walked into the Royal Astronomical Society's National Astronomy meeting in Durham, England, with data that would make headlines around the world. Banik, a researcher at the University of Portsmouth's Institute of Cosmology and Gravitation, had spent years analyzing something called baryon acoustic oscillations. These are essentially sound waves from the Big Bang, pressure waves that rippled through the early universe before it cooled down enough for atoms to form. When the universe cooled, those waves froze in place. They've been expanding with the cosmos ever since, leaving a distinctive pattern in how galaxies cluster together. Scientists use them as a cosmic ruler, a way to measure distances across the universe. Banik compiled 42 distance measurements from the past 20 years, including data from major surveys like SDSS, DESI, and DES. Then he tested whether a universe with the KBC Void fit the data better than a universe without it. The results weren't even close. A void-free model showed 3.3 sigma tension with the observations. The void model, just 1.1 to 1.4 sigma. In statistical terms, the void model was about 100 million times more likely than the standard model. 100 million times. Banik published these findings in monthly notices of the Royal Astronomical Society, and suddenly, the void theory that had been dismissed for years was back on the table. Here's why it works. If we're sitting inside an underdense bubble, the denser regions outside would exert gravitational pull on everything around us. Matter inside the void would be pulled outward toward the edges. This creates additional motion on top of the normal expansion of the universe. When we measure local expansion, we're not just measuring cosmic expansion. We're measuring cosmic expansion plus this extra outward drift. That's why our local measurements come out higher. We're literally being fooled by our own cosmic address. As Banik put it in an interview with phys.org, the Hubble tension is largely a local phenomenon. A local solution like a local void is a promising way to go about solving the problem, but not everyone is convinced. In 2019, Adam Rees, the same Nobel laureate whose measurements helped create the Hubble tension, published a paper specifically targeting the void hypothesis. Using 1,295 Type 1a supernovae, the largest sample at the time, his team concluded that supernova data was inconsistent at 4 to 5 sigma confidence level with the kind of large void the KBC model requires. They specifically called out the KBC Void model as disfavored at 6.2 sigma. Local structure does not impact measurement of the Hubble constant, the paper concluded. NASA has acknowledged the Hubble tension as a genuine mystery, but has not endorsed the void solution. Their official position mentions exotic particles, alternative theories of gravity, and early forms of dark energy as possible explanations. The void does not make the list. And there is a philosophical problem too. The void hypothesis requires us to accept that Earth occupies a special, rare location in the universe. We are not just anywhere. We are in one of the emptiest regions of the cosmos, positioned near the center of a bubble that is 7 times larger than typical voids. Professor Pavel Krupa at the University of Bonn, who worked with Banik on earlier void research, calculated the odds of this being coincidence. If standard cosmology is correct, the chance of finding ourselves in such a void is about 1 in a billion. That either means we got extraordinarily lucky or standard cosmology is wrong. Banik's response: our best theory of cosmology is wrong. That is a problem, but nature does not care about our theories. So where does this leave us? Right now, we have 2 competing explanations for why our universe seems to be expanding at different speeds, depending on how you measure it. One says our fundamental physics needs an overhaul. The other says we just happen to live in a cosmic desert that's been tricking us this whole time. The stakes are massive. The Hubble constant doesn't just tell us how fast the universe is expanding, it tells us how old the universe is and what its ultimate fate will be. Get that number wrong, and everything we think we know about cosmic history starts to unravel. Banik believes we'll have an answer within the next decade. The European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope will map galaxies with unprecedented precision. If the void is real, those surveys should confirm it. The key test is straightforward. If we're really inside a void, the Hubble tension should only appear when we look at the nearby universe. When we look at distant galaxies, far outside the void, the discrepancy should vanish. So far, the data from baryon acoustic oscillations supports exactly that pattern. But there's something else worth considering. If the void hypothesis is correct, it means the cosmological principle, the idea that no place in the universe is special, is wrong. Earth isn't just some random rock orbiting some random star in some random galaxy. We're positioned inside one of the largest empty regions in the observable universe. We spent centuries proving we're not the center of anything, And now scientists are suggesting we might be in the center of something after all, just not in the way anyone expected. Is the universe really playing tricks on us because of where we happen to be? Or is there something even stranger going on that we haven't figured out yet? Drop your theory in the comments. Because right now, the scientists don't have a definitive answer either.